So last video we talked about how to calculate net charge on a series of amino acids in a peptide chain. In this video we want to calculate the pI. Um, so pI is a certain pH at which amino acids, they have a net charge of 0. So they don't have a net positive charge or a net negative charge. So let me write down the definition of pI first. So pI is actually the pH when the net charge is 0. So it's the pH when the net charge is equal to 0. And in last video, we talked about how to calculate the net charge on the peptide sequence or the amino acid sequence, where I talked about how we can calculate um, the net charges on various kind of peptides, whether they have polar amino acids or charged amino acids or uncharged amino acids. But in this case, we want to talk about when they don't have a net charge or net charge of 0. So that's the pI. So in that case, amino acid are sometimes called zwitterions. So it's this new term. So they are called zwitterions. So zwitterions is nothing but um, the name for amino acids when they don't have a net charge. So at their pI, right? That's when they are called zwitterions. So let's see how we can calculate the pI value for certain amino acids or peptide chains. So I'll actually start from amino acids in this video, and then we can go on to calculate the pI values of peptide sequences, like we did for the net charge calculation that involved the Henderson-Hasselbalch equation in the previous videos. Okay, so let's start with, so there are actually 4 cases in pI calculation that we need to consider, because in the pKa, in the net charge calculation, right, there are also many cases. You can have a pH of, you can have basic pH, you can have a acidic pH, or you can have a pH around physiological pH like 5 or 6, right? But in this case, in pI calculation, we have actually 4 cases. So I'll go ahead and write down and we can discuss each one of them. So case 1 is actually when we need to calculate the pI value for amino acids that are over here. So these are all the amino acids that don't have an R group. I mean, they don't have a R group with any pKa values, right? I told you there are 7 amino acids that have R group that have their own pKa values. But for these other 13 amino acids, they don't have any pKa values for their R groups, because they're not ionizable like these 7 amino acids, right? So that's the difference. R groups for these amino acids over here, they cannot be ionized. So under acidic and basic conditions, these amino acids cannot be protonated or deprotonated. So that's the difference. So for these 13 amino acids, whether you're doing net charge calculation or pI calculation, we don't consider their R groups. We only consider the pKa values for their carboxy groups and their amino groups. So we can start with case 1, where I consider all these 13 amino acids that don't have any pKa values for their R groups. So we can start with that. So case 1, let's consider no R group pKa values. So instead of memorizing these 13 amino acids, you can memorize these 7 amino acids. As you know, 5 of them are really easy because 3 are basic and 2 are acidic. So you already know that 5 of them are charged at physiological pH. So histidine, lysine, and arginine are basic, right? They have a positive charge at physiological pH in their normal configuration. And glutamic acid and aspartic acid, they're acidic, right? They have a net negative charge at their normal configuration around physiological pH. And the only 2 you need to remember that are not charged under standard conditions under physiological pH are cysteine and tyrosine, right? Even though serine, threonine, and glutamine and asparagine, these 4 are also polar. They can also they are also in the category of cysteine and tyrosine, right? Cysteine and tyrosine and these 4, they belong to the polar category. But the only difference is that only tyrosine and cysteine can be ionized, right? So their R groups can be ionized. So that's why they have a pK value for their R groups, and these 4 and all of these 13 don't, right? So case 1, we consider these amino acids on the right side, okay, all the ones that don't have any pK values for their R groups. So for them, all you need to do is that for PI calculation, it's really easy. What you do is that you take the pKa of the carboxy group. So let's say I want to calculate the PI for glycine, right? I'll take the carboxy group pKa and the amino group pKa and divide them by 2. So I'll take the carboxy group and the amino group and divide them by 2. So C stands for the pKa for the carboxy group and N stands for the pKa of the alpha amino group. So that's all you need to do. So in this case, let's say for glycine, I need to calculate its pI, the pH at which the net charge for glycine would be 0. And this doesn't mean there is no negative or positive charges, right? We saw that in any amino acid at its normal configuration state around physiological pH, it would have a net negative carboxy terminal and net negative carboxy terminal and net positive amino terminal, right? So it's actually the balance of the positive and negative charges that makes the entire net charge of 0. So that's the PI, pH at which net charge is 0. So for glycine, it would be 2.34 plus 9.6 divided by 2. So that's all it is. It's that simple. So this can be around. So if you don't have a calculator like me, what you can do is that on any exam, if you don't have a calculator, you can just go ahead and approximate these, because usually when we were doing net charge calculations, right, we assume that carboxy pKa's are around 2. So you can approximate this to around 2. And we assume that the amino pKa values, these ones shown here in blue, they're approximated to be 10. So you will get, in this case, a PI of around 6, right? So if you can see the pattern, we normally assume a pK of 2 for the carboxy group and a pK of 10 for the amino group. Then in all the cases, you can see that we will get a PI of 6, and that's totally fine, because PI of all these, all these amino acids, these 13 amino acids with R groups that don't have their own pKa values, that are not ionizable, right? They'll have a PI of around 6. So all these 13 amino acids have a PI around 6. So that's how you can remember that. So if you already know, I showed you in the last video that for carboxy group, we approximate the pK value to around 2, and for the amino group, we approximate it to around 10, right? So you already know that for all these 13 amino acids, the PI would be always 6. So we don't even need to calculate that. So let's go ahead and talk about the second case. And our second case would be for these 2 special amino acids. Cysteine and tyrosine, as you know, they are not charged, but they still have pK values for their R groups, right? They come in this category. So tyrosine and cysteine are special cases. So let's see how we can tackle that first. So this will be case 2, right? And we are talking about tyrosine and cysteine. So in this case, tyrosine and cysteine, right? And for tyrosine and cysteine, it's actually the most complicated calculation for their PI, because what you're doing is that you're taking the middle value. In this case, for these 2 cysteine and tyrosine amino acids, you're taking the middle value in all their 3 pKa values. Okay, you take the middle value. So let's say for instance, tyrosine, you take the 9.11 or the pK value for the alpha amino group. In cysteine's case, you'll actually take the R group value, right? Because that's in the middle, 8.33, right? So let me write it down. You can take the middle value. So M denotes for the middle value. And then what you do is that you take the carboxy pKa. So you'll take the carboxy pKa and then divide that by 2. So that's actually how you do the PI calculation for these two amino acids. So this is actually the most complicated because first you're taking the middle value for the 3 pKas for tyrosine and cysteine. For tyrosine it was 9.11, for cysteine it was 8.33, and then you take their pKas of carboxy groups. So let's do it for cysteine. In cysteine's case it would be 8.33, right? So it would be 8.33 plus it would be the carboxy group pKa, right? That would be 1.71 divided by 2. So again, the same trick, you can, round it down to 8 and round this up to 2. So in this case, our PI is calculated to be 10 divided by 2, that's 5. So 5 is the the PI for cysteine. So this is for cysteine. Right? So that's how you do PI calculations for these two special amino acids. So you just need to remember tyrosine and cysteine that have this kind of calculation.